Hi students, this is Mr. Halpern. Today in this video we're going to talk about energy as a topic. This is the main focus of the unit. And we kind of shifted to talking about molecules and COVID-19. But we're going to shift back to energy as a topic. So where do we get energy? Well, it's really hard to talk about energy without talking about fossil fuels. Fossil fuels are exactly what they're called. They're from fossilized material, and we have it in three forms: petroleum, or as you might call it, oil, eventually when it's refined, or natural gas, like the main component being methane, if you remember methane, and then coal. They originate from biomolecules of prehistoric plants and animals, right? So fossils. And through pressure and heat and microbes converting organic material into oil, it takes so long that the fossil fuels are not considered to be renewable source. And I should put long, not link. So even though it's a process that constantly adds more and more, it's so long that we consider it a non-renewable. So inside of every energy molecule, like an oil, methane, for example, is stored energy. And we call stored energy potential energy. And an example is a spring that's really compacted. When you have a spring that's really compacted, it has a lot of potential energy. You feel that pressure, and then you release it. Okay? In chemical bonds, we're talking about potential energy. When we break off those bonds, we release that energy. So those bonds hold potential energy. Conversely, once we release that energy, it does something. It's energy in motion, right? In action. And so the spring is released, or we burn the fossil fuels and break the bonds and release that energy-rich molecule. And as a result, the reactants, the ones that are on the left-hand side of the equation, rearrange into more stable, lower energy, typically, products. Particularly when we're talking about the rearranging of atoms for fossil fuels and burning them, we are going to talk about reducing the amount of energy. And what do we see when we see a release of energy? We might see some heat given off. You might see a flash of light. Think about, again, burning a fossil fuel, like a candle, for example. Potential energy has three different types: elastic, like a rubber band or a spring; gravitational, like a rock that is sort of against gravity on a higher perch that could fall; and then chemical, like in lithium-ion batteries. And then it gets converted into kinetic. Let's look at an example here of energy conversion. So step one, first off, we need to make sure that we know that our molecules are written out in the equation. As you can see here, we have methane here. We have a little bit of oxygen, and this gets converted into its individual pieces: carbons, hydrogens, and oxygens. Okay. When energy is added to a chemical reaction, it's called an endothermic reaction. As you can see in the equation you have here, you have energy on the left-hand side. Okay. Activation energy is the amount of energy needed for a reaction to take place. And really what that means is the amount of energy it needs to break apart the bonds. So if your reactants are here, for example, right here, the activation energy is the amount of energy it takes to break apart the bonds. Sometimes you can add a catalyst to your reaction, which will decrease the amount of activation energy that you need. So it will decrease this amount of activation energy. Acids are often used as, or bases are often used also as catalysts. So activation energy, by the way, is represented as E sub A, energy activation. And then the step 2, the second part after you break the bonds, is you make new bonds. And this process is energy releasing. So when we're making new bonds, we release energy, and that's called exothermic. And exothermic is releasing. So if you think of exit, right, release, leaving. And as you can see here, you now have, if you look at the full formula here, you have energy being added in order to break apart the bonds into its individual atoms. And then once you have the individual atoms, you can reform them into new molecules and energy is released. So in the case of methane and oxygen gas, you break those apart into atoms and now you have, anyone? This is a carbon dioxide and water molecules. So over here you have an endothermic reaction. If you see that an energy diagram shows that the reactants start at lower energy and eventually ends with the products having higher energy, you know that energy was put into the reaction more than was taken out, right? And as you can see here, there was energy put in, as you saw here, and there was energy that was released, as you can see the sort of hump going down again, and that's exothermic here, energy coming out. In this particular example, this would be overall an endothermic reaction because the difference between the reactants and products is that the products are higher. Conversely, if we talk about an exothermic reaction, that means that the amount of energy that was put in is less than the amount of energy that was given off or released. As you can see then, the reactants are higher than the products, so overall the net change of energy is decreased or it's released. Now, you might see in this particular, these diagrams, a delta H. This delta H is a way of measuring or saying what the energy is doing, okay? A delta H is a measurement of the difference between the reactants and the products. This is another visual way of representing this reaction here. In the case of the reaction between molecules, you have methane and you have oxygen gas forming carbon dioxide and water. And overall, whenever we do a combustion reaction, we have a net loss of energy, right? Always we have combustion reactions being exothermic. So you're going to see reactants higher and products lower. Again, energy is added so we can break apart the bonds, and then energy is released to reform those bonds. And as we said, overall, this is exothermic. Okay? Burning of methane or any other fossil fuel is exothermic. It's ultimately releasing. And that delta H that was mentioned above is the amount of energy released or absorbed in an entire chemical reaction. If you notice, you have a net decrease of energy. So we're going to have a negative delta H for exothermic and a positive delta H for endothermic. We're going to do more practice with this in class. So if this is a little bit confusing, no worries. Hopefully you get some notes down on page so we can talk about this tomorrow.